Alright, we begin a new chapter with the little Rick Derringer and Rock and Roll Hoochie Coo, and also we are going to look at another way, an alternative way to graph ordered pairs on the axis, on the plane. Now, in the past we've used rectangular coordinates and we had the ordered pairs x, y. And that's really been everything that we've needed all up to this point. But there is an advantage to learning a second method using what we call polar coordinates. And the polar coordinates are, and notice I use a semicolon, then theta. Now the textbook uses a comma, but I like to use a semicolon so that you can readily see the difference between the traditional ordered pair with the rectangular coordinates and this new system of the polar coordinates. Now, typically sometimes new things are kind of not treated well, not accepted well. I know that that's the case for many people, but I think you will find in certain circumstances that learning to be able to graph using polar coordinates and the polar coordinate system is going to be to your advantage. The polar coordinate system consists of a finite point, O, which we call the pole. Usually we refer to it as the origin on the coordinate system, the rectangular coordinate system, and a ray called the polar axis with the endpoint at the pole. And it's typically in the positive direction of the horizontal axis. So if you draw like an x and a y axis, the pole is at the origin and the polar axis is the positive direction of the x-axis. Each point, which we'll call point P, in the plane is defined by an ordered pair in the form again, r semicolon theta, where r is a directed distance from the pole to the point. So that's this distance right here. Notice how I tried to draw the polar axis kind of horizontal, and notice here the way I have my angle theta. If r is greater than 0, remember it's a directed distance. If r is positive, greater than 0, then point P is located r units from the pole in the direction of our angle theta. But if r is negative, so we have a negative polar distance there, then what we do is we use point P is located the absolute value of r units from the pole, but in the exact opposite direction. Notice theta plus pi, or theta plus 180 degrees. So instead of going out this way, we would come back this way in that direction. And if r is equal to 0, that means that the point is on the pole itself. It's at the origin. Now, theta is also a directed angle. We have a directed distance. We have theta being a directed angle from the polar axis to the line there, OP. Contains the point and contains the pole. If theta is positive, greater than 0, we measure it counterclockwise, kind of like we did when we were talking about angles in standard position. Counterclockwise was positive, clockwise was negative. If theta is less than 0, then we measure clockwise from the polar axis. And I like to refer to as r and theta as the polar distance and the polar angle. So instead of saying, okay, I'm right here at the pole and I want to get to right here, how much to the right and then how much up do I go? What I'm thinking instead is, at what angle would I line up with that point, and then how far out to get to that point? That distance, that's your polar distance. That angle, that's your polar angle, r and theta. Okay? Now, we're going to plot the points that I have here, and all these are polar coordinates. We're going to plot them on polar graph paper. Now, you have to use polar graph paper. You don't want to try to draw this out freehand on a piece of paper itself, because you'll see that because we're looking at the angle, we need guidelines to help us to get the angle as exact as possible. So what I have here is an example of polar graph paper for the board. And hopefully this will stay in the tray here okay. Notice you can see the emphasis of these two axes here being very similar to the x and the y axes, but this is when our angle is 0 or all the way back to 2 pi, and our angle is pi over 2 or 90 degrees straight up and down. And you can see that I've got this broken into groups of 15 degrees or groups of pi over 12 radians. And they've even been broken down even more exact. You can find polar graph paper. Let me scoot this over. I'm going to have to scoot this over just a little bit. But you can find polar graph paper not only by going and doing a search and finding it that way and then printing yourself some copies. You can buy it at the store, and I also have it built into the class. So if you go to the link for the graph paper, you'll see polar graph paper up there as well. Print yourself out some sheets of it. You're going to be doing a little bit of graphing. Now, the first ordered pair that I'm going to graph is a polar distance of 3 and a polar angle of 5 pi over 4. All right, notice that these are both positive numbers. So I'm going to go this distance counterclockwise, so that's over to here, 5 pi over 4, right to the pole there, and I'm going to have a distance of 3. Now, to make sure that I know that my distance is 3, I'm going to set a scale here, and I'm going to say that this first circle represents a unit of 1, a unit of 2, a unit of 3, a unit of 4, and so on. So that will be how I determine the R. This is my theta. I'm coming out this way, a distance of 3 units. So 1, 2, 3. I'll put my pointer right here. I'll make it nice and big so you can see it. And that's the answer to part A. That's not so bad. Now, if you start thinking about this, you say, well, wait a minute. I know that I can also have other angles that are putting me in the same. Some coterminal angles. There's probably more than one ordered pair in polar coordinates that graphs the same point, and that's true. There are infinitely many pairs, ordered pairs, because of coterminal angles. All right, for part B here, I have 4 and then I have negative 7 pi over 6. This time my angle is negative 7 pi over 6, so it's going to be clockwise. Now 7 pi over 6, this is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6 would be in this direction right here. Now I know it says 5 pi over 6 here, but that's because that's if I go counterclockwise. If you subtract 2 pi from this, you will get negative 7 pi over 6. So this is the angle that I want right on here, and I want a polar distance of 4. So 1, 2, 3, 4, and I put a point right here, and that's B. All right, now I have 2.5 and 4 pi. 4 pi means you're going to do 2 complete revolutions, but you're going to be at the same coterminal angle as 0 radians or 0 degrees. So I'm going to go right out here on the polar axis, and I'm going to go a distance of 2.5. So I think you can still see this. I don't think it's cut off quite yet. I'm going to go 1, 2, and then you approximate best you can 2.5, and that's C. Okay? And you should still be able to see that. Part of my polar graph is got cut off because I put these too far to the right. Okay, one more to go here. This time it's got a polar distance that's negative. Now remember, if it has a polar distance that's negative, it's going to go in the exact opposite direction. It's as if you add or subtract pi to this. Now if I subtract pi, 4 pi over 3 minus pi, which is 3 pi over 3, would give me pi over 3. That would be the direction I'm going. 4 pi over 3 is out this way. But because my polar distance is negative, I'm not coming out this way. I'm going the exact opposite direction at pi over 3. And a distance of 3, absolute value of 3. So I'm going to go 1, 2, 3. Hopefully this is still on the screen, and here's the answer to D. Now, if I ask for a bunch of ordered pairs to be graphed, you don't have to waste a whole sheet of polar graph paper for one point and then another sheet for a second point. You can do what I did here. I put them all on the one grid, and I just labeled them so that I knew which one corresponded to which part of the problem. Now, we're going to do a lot more than this, but this is the introduction to graphing points using the polar coordinate system. You kind of have to get used to it. It's a little different. It's like once you learned how to print, and then all of a sudden they taught you a cursive or longhand. It's like, well, wait a minute, why do I need cursive? I can print. Well, there's a time when printing is good, there's a time when cursive is good. There's a time when rectangular coordinates fit our need, and then you'll find out that there's times when polar coordinates better suit our needs. So kind of get used to it.